Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture Series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome. It's a great pleasure to introduce Amie Wilkinson, today's Distinguished Lecture Series speaker, who will be telling us about asymmetries of dynamical systems. A beautiful and deep piece of work she'll allude to during the course of her talk is this problem that was posed by Steve Smale as one of the 20th century problems for 21st century mathematics. And it basically says that if you have a generic dynamical system, then its centralizer is trivial. She'll explain what all this means during her talk. I should point out that she, along with Christian Bonatti and Sylvain Cravessier, had solved this problem completely in the C1 case. Professor Wilkinson is the recipient of the 2011 Satter Prize. She was an invited speaker in the International Congress of Mathematicians in 2010 in India, and she won the Lévy-Conant Prize for Exposition in 2020. Without further ado, over to Amie.
Hi there, my name is Amie Wilkinson from the University of Chicago, and I am here to tell you about a subject that's interested me for a while, and that is asymmetry in dynamical systems. So before I tell you what asymmetry in dynamics mean, I have to tell you what symmetry means. So symmetry is a term that's usually applied to as a property of objects. So for example, if we take a snowflake, which is a famously beautiful symmetric object, a symmetry of this is a motion that leaves the object unchanged. An actual snowflake will not be exactly the same if you apply symmetry, but an idealized snowflake will. So here's an example of a symmetry. A rotation by 60 degrees leaves this snowflake unchanged. And I could similarly rotate by some multiple of 60 degrees, and that's another symmetry. There's one more symmetry, though, that's maybe a tiny bit less obvious. If I pick the snowflake up and pull it out of the plane and flip it over, and there it is flipped over once, flipped over again, that single flip is also a symmetry of the snowflake. So the symmetries of an object form a group. And in the case of this snowflake, it's the dihedral group, which is generated by two generators, A, which is a rotation by 60 degrees, and B, which is the flip, and they satisfy these relations. So in general, and it was very natural that the symmetry should form a group. And in fact, the notion of group comes from the study of symmetries. So the associativity rule and so on are natural properties that symmetries should have. For example, the inverse of a symmetry should be a symmetry. Doing nothing, the identity is a symmetry, and so on. Okay, so now what do I mean by a dynamical symmetry? So first, let me tell you just a little bit what I mean by dynamics. So the type of dynamics I study, I'm going to kind of jump ahead a little bit, is the study of smooth dynamical systems. Okay, so there's some calculus involved. So let's fix an integer r that's at least 1, or it could be infinity. We say that a CR, or smooth dynamical system, is, all we mean by this is a CR map F from a manifold M to itself. Now, if you are a little uncomfortable with the idea of manifolds, you can think of M as being the plane. You can think of M as being the surface of a sphere or the surface of a donut, and so on. And CR just means R times continuously differentiable. So a CR, why do we call this a dynamical system? So dynamics is the study of motion. And so there's a concept of time. And a map F from a set X to itself, or a manifold M to itself, gives a way of generating motion over time. So if we were to take, for example, a point X inside of our M, so we think of M as maybe a state space and X as a state, then by applying F repeatedly through a process we call iteration, we can go to a point F of X, and we can apply F again and get to a point F of X, which we call F squared of X. And so on. We can just keep applying F, and the points that we obtain in this fashion, the states, to be thought of as the position, new state over time. So for example, F of X should indicate where X is after 1 unit of time, F squared of X is after 2 units of time, and so on. Like composing F itself K times, so we call this F to the K, we obtain a new dynamical system, and it tells you where you are after K units of time. So this sequence of points I produce by applying F is called the orbit of the point X under F. If F happens to be invertible, I haven't assumed this, we could also go backward, and we could talk about F inverse of X, F inverse squared, or F to the minus 2 of X, and those would be the past orbit of the point X. Okay, so now we want to talk about what is a symmetry. So a symmetry, we want symmetries to form a group. So we want symmetries to be the inverse of a symmetry to be a symmetry. Okay, so the natural class, since we're talking about smooth dynamics, to look at is the set of CR diffeomorphisms. And that's just a CR map with a CR inverse. So a CR diffeomorphism is a symmetry of F if this simple relation holds: F composed with H equals H composed with F. And I will kind of give you some indication why that makes sense to think of this as a symmetry. So equivalently, we can write F as H composed with F composed with H inverse. So H can be thought of, a symmetry can be thought of as a change of coordinates that preserves the dynamics, a smooth change of coordinates. And it has the nice property that if I iterate a bunch of times, so if I take F to the K, that's equal to H composed with F to the K composed with H inverse. Okay, so it's natural in the sense that it preserves time in that sense, okay? So as with symmetries of an object, symmetries of a dynamical system form a group. And we're going to call this the dynamical symmetry group. It's also sometimes called the centralizer in the special case where F is also a diffeomorphism. So what is the dynamical symmetry group? It's just the set of symmetries of F. And they form a group because we can compose two symmetries to get a symmetry. That's an easy thing to see. The identity is a symmetry, right? F always commutes with the identity map. And because symmetries are invertible, it's not hard to see that if H commutes with F, then H inverse also must commute with F. So in this sense, and so we could see this by conjugating, so putting H inverse times this H, or sorry, putting H inverse on both sides like this, on both sides, we get that F composed with H inverse equals H inverse composed with F. So they form a group. Okay, so we're going to call this the symmetry group and denote it S of H. Okay, this is a subgroup of the space of CR diffeomorphisms of M, which is itself a group. In the case where our dynamics are smoothly invertible, so when F itself is a diffeomorphism, then any iterate of F, well, F itself is a symmetry of F, right? Because F composed with F is F composed with F. And in fact, all the iterates of F are also symmetries of F. And so all the powers, F to the N, where N could be an integer, lie inside of the symmetry group of F. So the symmetry group of F contains, as a subgroup, the group generated by F. And in fact, it's a normal subgroup. That's an exercise, very, again, easy exercise that you could do before we meet to talk. Okay, so symmetries. Why symmetries? Well, I said the sort of fundamental object of study in dynamics is orbits, which indicate kind of the past and the future of a starting point or a starting state of the system. So let's see pictorially why symmetries map orbits to orbits. So here's a point X in M. If I apply F as before, I get F of X. If I apply H to F of X, I get H of F of X. On the other hand, I could apply H to X and I get H of X. And if I apply F, I get F of H of X. But because these are two, one and the same, this is the single point. So F takes H of X to H of F of X. Okay, so simple commutative diagram. And now we can iterate this simple commutative diagram and get the following picture. So I could take a point X, there's F of X, there's what I was calling F squared, and so on, F cubed. Okay, so we have the full orbit of F. And on the other hand, I can take X to H of X and look at the full orbit of H of X. And the previous picture says, since H is a symmetry, it literally will take one orbit to the other. Okay. So symmetries are beautiful because they help you kind of nail down information of a dynamical system. So if you know you have a symmetry, that symmetry can tell you something about invariant quantities or sets associated to that system. So an example is the set of periodic orbits. So these are states that return to themselves under iteration. And let me just spell out what I mean. So if we let fix of F just be the set of all what we call fixed points, so the set of X such that F of X equals X, okay? Then if X is in fix F and H is a symmetry of F, then notice if I apply F to H of X, this is H of F of X. F of X is X, so this is H of X. And so therefore, H of X is also in fix F. And since H is invertible, we can go in the other direction and we see that H of fix F is fixed F. So all the points, all the equilibria of F are preserved by H. And similarly, I could take an iterate these are what we call periodic points of period K. And the same argument applies because H commutes with F to the K. And so the periodic points, which can often capture a lot of information about the dynamics, have to be preserved by any symmetry. And if you know what these things mean, so multipliers are eigenvalues of derivatives around periodic points. Stable manifolds are kind of a basic object of study for periodic points. If you know what these are also preserved by symmetries. And similarly, invariant measures, which I've written over, but if you know what an invariant measure is, any invariant measure is taken to an invariant measure for such a system. And here's an example I'd like to focus on a little bit. So these are the non-wandering sets for the dynamical system. So the non-wandering set is where the interesting dynamics happen. What does it mean to be an element of a non-wandering set? It just means the following. So X is non-wandering if for every neighborhood U containing X, there exists some integer n greater than 1 such that f to the n of u intersect u is non-empty. Okay, so that means any neighborhood comes back to itself. There's something nostalgic about the forward orbit of the point X. So it's not hard to see that the set of all non-wandering X is non-wandering if this holds. It's not hard to see that the set of non-wandering points closed because the complement is open, the set of wandering points is open. And if H commutes with F, let's just do the little exercise. So suppose X is non-wandering, and H is in this for F, implies, well, if I take any neighborhood U containing H of X, so we want to show H of X is non-wandering. So if I take a neighborhood H of X, well, that means H inverse of U is also an open set, and that's an open set containing X. And so there exists an N such that F to the N of H inverse of U intersect H inverse of U is non-empty. And now, because H commutes with F, we get that H inverse of F to the N of U intersect U is non-empty, right? And U is a neighborhood of H of X, F to the N. So this implies in particular that this is not empty. And now this implies that H of X is also non-wandering. Now, in the case where F of Z, well, let's back up for a second. In the case where F is a polynomial, a complex polynomial, so F of Z is some Z to the K plus so on, a complex polynomial like that, the set of non-wandering points for F has a name, and this is called the Julia set of F. And it is a compact, you can show a compact subset of the complex plane. And now I want to look at the Julia set. So any symmetry, let me just summarize what it said. Any symmetry of the Julia set is also a symmetry of the Julia set. It takes the Julia set to itself. So we've gone from symmetry of a dynamical system to symmetry of an object associated dynamical system. And I want to illustrate this with a few examples because we can make pretty pictures. So consider this polynomial that I've written down. I claim that the map H of Z equals zeta times Z, where zeta is an 8th root of unity, is a symmetry of this dynamical system. So I worked it out for you here. So I take f of H of Z, that's f of zeta times Z, If I plug it in, I get the following expression. And now using the fact that zeta to the 9th equals zeta, I can rewrite it in this way and pull out the zeta. And now you notice that this is zeta times f of z, which is h of f of z. And so the symmetry group contains all the iterates of h, and that's isomorphic in this case to z mod 8z. And so we should see in the Julia set a rotational symmetry of order 8. Well, here's a picture of the Julia set, and there it is. There's a symmetry. I just rotated through the pi. All right, let's do another example. So for this example, we again have a symmetry of the form omega times z, where omega is x root of unity. It's the same calculation. But then there's one more thing you can notice here, which is that the coefficients of this polynomial are real. And that means that if I consider the map G of z, which is the combination, which is of order 2, this is also a symmetry of F. So that's an exercise. And so the symmetry group for F contains these two elements and contains the group they generate. And so we should see a dihedral or snowflake kind of symmetry in this Julia set. And sure enough, there is a snowflake Julia set. Okay. So to give some more example or say a little about symmetries, it's convenient to introduce the notion of continuous time dynamical systems. So dynamical systems we've considered, we iterate time in discrete units. And so time is discrete, if you like. But we could also consider dynamical systems where time evolves in a continuous way. So such a dynamical system is called a flow. And we can formalize the properties that a flow will have to be a dynamical system analogous to iteration of a single map. So we say that a CR map from R cross M into M is a smooth flow if it has the following properties. So the first property says, so phi sub s is what we use to indicate phi sub sx. This is just notation. So this is the map under s units of time. And so we want that if we evolve by s units of time and then t units of time, it's the same as evolving over s plus t units of time. And we also want that at time 0, the map is the identity. Okay, so those are the two properties that our flow should have. And if we fix a unit of time, like say 1, then the time 1 map in that case is going to be a diffeomorphism. So exercise to you is, why is this a diffeomorphism? In other words, why must it have a smooth inverse? So if I take the time 1 map of a smooth flow, I get a diffeomorphism called the time 1 map. And I want you to note that the notion of iteration of time for that diffeomorphism coincides with the evolution of time for the flow. So if I take the nth iterate of the time 1 map, that's the time n map of the flow. So here's a question I want to address a little bit in this talk, which is, which diffeomorphisms embed in a smooth flow? So in other words, given f, does there exist? Okay. Given f, does there exist a flow phi t such that phi f is the time 1 map? So there's obvious topological restrictions. So if f is not homotopic to the identity, if it can't be deformed to the identity, it certainly cannot be the time 1 map of a flow. That's a necessary condition. So if you like, you could ask the question, which diffeomorphisms that are homotopic to the identity map embed in smooth flows? And I'll give you a partial answer to this question a few slides later. But continuing with smooth flows and their symmetries, I want to recall for you that any smooth flow on a manifold has associated to it a vector field. And that vector field is just the derivative, if you like, of the flow. Sometimes called the generator of the flow. So we'll call that V. And so it's obtained by just differentiating phi t with respect to t and setting t equals 0. So if we take an orbit of this flow and we take any point on this orbit and we differentiate with respect to time, the tangent vector, the velocity vector we get is, by definition, if this is x, this is v of x. That's the velocity vector. And so if you want a picture of how to evolve a continuous time dynamical system or a flow, imagine that you have a vector field, and then to determine the trajectory of the orbit under time, you just follow that vector field. So kind of conversely, if I have any sufficiently nice vector field given by a system of ordinary differential equations, given a vector field, we can generate a flow by considering the associated ordinary differential equation, which looks like this. Okay, so what's a symmetry of a flow? Well, a symmetry of a flow is another flow, another continuous system that commutes. And we ask that this happens for all units of time. So a flow is always the symmetry of itself, clearly, by definition of a flow. And I want to note that if I have a symmetry of a flow and I take the time one map of the flow, right, so that's a diffeomorphism, then the symmetry group of the diffeomorphism is going to contain that entire flow. And so in particular, it's going to be uncountable, right? Because the flow, I mean, unless this is like a trivial flow, it's going to be large, right? Okay, so in particular, since the flow commutes with itself, the symmetry group of a flow, time one map of a flow contains the entire flow. So that's something you need for diffeomorphism to equal a time one map. It has to have inside of its symmetry group a flow. Okay, so one map of a flow has a lot, or at least extra symmetry. So keep that in mind. We'll come back to that question. The theme of this talk is that symmetries of dynamical systems are special. And I'm going to illustrate that in a few ways. So first of all, in physics, this is not anything new. This is not new stuff, but it's interesting. Symmetries can correspond to conserved quantities. So given a conserved quantity of a physical system, you can produce a symmetry of the flow and vice versa in a way that I will make precise. The next is involves a question of Steve Smale, sometimes called a conjecture. And that says that the typical dynamical system should have minimal symmetry. Okay, minimal meaning just like the iterates. And the third is that a little bit of symmetry can imply a lot of symmetry. And this is something I'll call symmetry rigidity. And I'll mention a little current work. Okay, so let's do the first. This is the theorem of Amie Noether, the German mathematician. So Noether's theorem says in words that the symmetries of a physical system are going to correspond to conserved quantities. And an example that's kind of a little more advanced than what I'm going to give is that of a top, a spinning top. So in these three pictures, we see a top that's being spun, but we've just rotated where it starts. We've rotated the angle with vertical. And otherwise we spin it, and we imagine we've spun it exactly the same way. And that we're not subject to any forces like any frictional forces that will make the top fall or anything like this. And the thing about this spinning top is quite clear looking at it. If I start spinning it over here at a certain velocity, or if I rotate my frame of reference and I start spinning it here, I'm going to get the same evolution, but just corrected by this rotation. And this rotation is a symmetry of the top. On the other hand, there's a quantity that you can measure associated to a spinning top called the angular momentum. And that's a quantity that is preserved under the spinning of the top. Angular momentum is preserved. And those two things correspond to each other, those two facts. So quickly, what are Hamiltonian dynamics? So a Hamiltonian on R2n is a function, just a function from Rn to Rn, cross Rn into R. And the value of this function is going to represent, or you can think of it in physics as representing the total energy physical system. Here, the Q1 through Qn coordinates are supposed to represent spatial coordinates, either of a single particle or maybe a bunch of particles, depending on how big n is. Pi are momentum or velocity, if you like, coefficient coordinates. So if the mass is 1, you can think of the pi's as just being velocity. And H should be a smooth system. So for example, here's a simple kind of high school physics example. If I take a spring, and there's no gravity in this example, but I take a spring at rest and I put a mass, say of mass 1 at the end of that spring, and I measure position. Here there's just n is 1. I measure position from rest. Okay. Then the total energy of this system, so there's going to be two factors. There's the momentum and there's the position from rest. If the spring constant is 1, then the total energy is going to have two components. So this 1/2 q squared, so 1/2 q squared is going to equal the potential energy from the spring, and the 1/2 p squared, or 1/2 v squared in this case, mv squared, since m is 1, is going to be the kinetic energy. So associated to any Hamiltonian of this type is something called the Hamilton's equation, sorry. So there's a principle of least action that's associated to this Hamiltonian via a Legendre transform to a Lagrangian system. And the trajectory of the system like this satisfies the principle of least action if and only if these following ordinary differential equations are satisfied. And these are called Hamilton's equations. So the equations give us a vector field, and I'll give you a quick example. The vector field generates a flow on R2n. And here's another exercise. This is the chain rule. Try this if you like with n equals 1, just to see how it works. N equals 1. The flow that is generated by this vector field is going to conserve this energy H. So this is an invariant quantity always associated to a Hamiltonian flow. Along an orbit, the energy does not change. The total energy does not change. It's determined by its initial state. So let's return to our example of the spring. Here, the energy is 1/2 q squared plus p squared. So we can write down the associated Hamiltonian equation, which gives us a vector field. And if I do this, if I've done my calculus correctly, this is the vector field. And now we can draw a picture of this vector field. It's a clockwise rotational vector field in the plane. And if we solve these differential equations, we get the following flow. So it's a rotational flow. It rotates the flow, and orbits are going to be circles. The speed is proportional to the distance from the origin. And there's a conserved quantity, namely this energy. And notice that's consistent with the orbits being circles, because energy equals constant gives you a circle. So here's a picture of that flow. You can see the spring going back and forth. So a little exercise is to figure out why that green thing is going counterclockwise instead of clockwise. And the hint is think about the orientation of the axes. Okay, okay, so Noether's theorem tells us the following. It says that if I have a Hamiltonian flow and it commutes with another Hamiltonian flow, so I have the symmetry that is a Hamiltonian flow, well, that says that the Hamiltonian for the second flow is actually a conserved quantity for the first flow. So like with the top, there's a Hamiltonian that generates this rotation. And that Hamiltonian is called the angular momentum. And since the flow, as we saw before, the flow commutes with the dynamics of the spinning top, that means that the angular momentum is also conserved. Okay, so this is the statement, or one statement of Noether's theorem. There are more advanced ones as well. But conversely, if I have a conserved quantity, I know there's a conserved quantity, it gives me a symmetry of the flow. So we can conclude that the symmetries of a Hamiltonian flow are special. They correspond to conservation laws. Okay, now I want to turn to Smale's question. So this was posed by Steve Smale probably around the turn of the century on a list of questions for the 21st century. But he's interested in this question for a while. So the question just says, does the typical diffeomorphism of a closed manifold have only trivial symmetries? So in other words, the symmetry group of F is actually equal to the powers of F, of the iterates of F. Now, what is this question? What does this term typical mean? So he kind of left it open, but there's several ways you could think of a typical dynamical system. So the space of CR diffeomorphisms of M, we can think of as the universe of dynamics on the manifold M. And it carries a topology. So we can talk about two CR diffeomorphisms being close. Well, if they take a single point, they take the points nearby, their derivatives are close, and all of their derivatives up to their rth order derivatives are close. So there's a natural topology. And so we could say that a typical diffeomorphism is one that any diffeomorphism can be approximated by. So that would be a notion of a dense set of diffeomorphisms. Or you could talk about their generic, what we call generic properties. So we say a property is generic among the diffeomorphisms of a manifold if there's a countable intersection of open and dense sets, so that the property holds. So it's a residual set of diffeomorphisms where the property holds. So that's even larger than being dense. So for example, in the real line, a dense set is the rational numbers, but a residual set is the irrational numbers. So it's a large set. Okay. So very early progress was made on this question in the thesis of Nancy Capel, who was a student of Smale. And she proved that if I take any R, like R equals infinity, as long as it's bigger than 1, then the typical diffeomorphism has only trivial symmetries. So here, typical is a very strong notion. It means that it holds for an open and dense set of dynamical systems. So it's a very strong notion. It's only true for 2 and higher. It's actually false for C1. But this left open the question, what about in higher dimensions? Now, there's been partial work among certain classes of dynamical systems, and the evidence seems to point toward the truth of Smale's conjecture, or a yes answer to his question. And in fact, in the C1 topology, if we just look at C1 diffeomorphisms, the conjecture holds. So this is work of myself and Christian Bonatti and Sylvain Crovizier, maybe about almost 15 years ago at this point. So for any closed manifold, meaning compact and without boundary, the C1 generic diffeomorphism has only trivial symmetries. And so the symmetry group of F, just to remind you, is equal to all the iterates of F, and there's no other symmetry, which is what you would expect. I mean, you don't expect to see Why would you expect to see a kind of random dynamical system with a lot of symmetry? So this does actually give an answer to my earlier question. The C1 generic diffeomorphism does not embed in a flow. So even if it's homotopic to the identity, if the iterates of F are the only symmetries, it can't embed in a flow, which would have an uncountable set of symmetries. Now that question was actually answered quite a bit earlier, just the embeddability question by Jaco Pallas, sometime in the 70s, I believe. But if we ask for R being greater than 1, the question is still open, and it seems to be a very difficult question. And in fact, even this question of embeddability, the one that was answered by Pallas, appears to be open for R greater than 1. Okay. And then finally, I just want to say a few words of what I call symmetry rigidity, which is closely related to the type of questions I'm interested in. And so what do I mean by that? Well, basically, we know that at least in C1, the typical dynamical system does not have extra symmetry. So what if we have an atypical diffeomorphism? How atypical is it? What if you have extra symmetries? So symmetry rigidity is kind of a property, if you like, of a class of diffeomorphisms in which a little bit of extra symmetry implies a lot of symmetry. So there's a nice example with Julia sets, actually. So this is a result due to Yusheng Luo. Contained in work of Lusheng Luo, says the following. So if I have a polynomial, the complex plane, and it has a symmetry, just a single symmetry of infinite order. So in all the examples we saw, the symmetries were finite order, right? The snowflake group, the rotation group. But suppose that I have a Julia set that has like infinitely many symmetries. Then the Julia set can only be one of 3 things: the circle, an interval, and the whole plane. So what's an example of a Julia set? A polynomial whose Julia set is the circle. It's not a nice circle, but you can check for z goes to z squared. The only recurrent points, the points that recur, are exactly the circle. Everything else either goes under iteration to the origin or out to infinity. Or the interval. An example, an example would be the polynomial z maps to z squared minus 2. And of course, it could be the whole plane because F could be the identity, but that's it. So in smooth dynamics, it's a little trickier. There's kind of a bigger world of symmetries that one has to consider. But I have a project going on right now. We've been working on this for some years now with Daniela Damjanovic and Dishang Xu. And just to give a kind of caricature of what we've shown. So inside the group of C infinity diffeomorphisms of certain manifolds, there exists very symmetric dynamical systems. These are ones, we call them homogeneous dynamical systems. They're ones that are in algebraic nature. And what we've been studying is, so these have a lot of symmetry, typically, much unusually high amount of symmetry. And what we've been studying is, what if we take such a dynamical system and we perturb it? So, well, you can perturb, sort of change the dynamics a little bit, and it's actually the original system in disguise. So there's a smooth change of coordinates where you get the same system. But suppose we make a genuine perturbation that's not smoothly conjugate, and the type of result that we show for some such systems is that if you've actually changed the dynamical system in any meaningful way, suddenly there are no symmetries. Or there's more kind of refined results that we can show where you have a lot of symmetries, and if you perturb, you can have fewer symmetries, but we can say exactly what symmetries you have. And if you have maximal symmetry, then you are actually one of these original algebraic systems. So that's just a flavor of some of the questions in symmetry and dynamics that interest me right now. And I look forward to speaking with you in person in a follow-up. And thank you very much. Bye-bye.